Hello? Can you hear me?
Yes, perfect.
Yes, Professor. I'm here.
Okay, if everyone's back here, then let me continue. So before I go to the next topic, which is, there are other things, but let me, this is going to what is called the sufficiency condition, because we derived the sufficiency condition in the previous chapter, and now we want to derive the sufficiency condition for this new problem, extended version of the problem that requires some couple of other concepts. Okay, but before I go, I just wanted to mention to you that I talked about the issue of existence and why most people in our field don't appreciate why the other guys in math worry too much about it, and they should. And the reason is that if you assume existence and it doesn't exist, then you can do whatever you want. You can prove anything, any garbage you want to prove. So here's a proof of something that I want to show you. So let me see if you can see it. Can you see this picture here that I show you?
we can see some part of it.
Do you see? Let me see. Do I have to move this way or this way? Like this?
Yes.
Okay. So if you see the first line, it says theorem. It says n equal to 1 is the largest number. Can you read that?
Yes.
So now I'm going to prove that. So the first is the theorem. Second part is the proof. The proof, it says let n be the largest number. Because that's how we prove, right? We start with some let, right? So if n is the largest number, the next thing says n has to be bigger than equal to 1. Do you see that n bigger than equal to 1?
Yes.
Well, if n is bigger than equal to 1, then every number that is bigger than equal to 1, its square is bigger than equal to 1, right? If there's a number which is bigger than 1, then the square is bigger than that number, right?
Yes.
So the next line says n squared is bigger than n, which in fact is bigger than equal to 1. But n is the biggest number, so n squared has to be equal to n, right? Because we said let n be the biggest number, so n squared has to be equal to n. And n squared equal to n is an equation that has only two solutions, n equal to 0 and n equal to 1, right?
Yes.
0 cannot be big, so n equal to 1 is the biggest number. Proof complete. Where is the flaw in the proof? Obviously, the theorem cannot be correct. Where did I make a mistake? Which line where I made a mistake? Anyone? So the mistake is first line. Let n be the largest number. The mathematics people would tell you that n equal to largest number is an optimization problem. You have to first prove that there exists the largest number before you go to the next line. And we did not prove that n is that there exists the largest number. We did not prove the existence of a largest number. In fact, we cannot do it because there does not exist any largest number. Because you give me a number, I give you a number bigger than that, right? You give me a trillion, I give you a zillion. If you give me a zillion, I give you a quadrillion. I can give you a number bigger than whatever. If you give me 100, I give you 101, right?
Yes.
So there does not exist any largest number. But if you assume it, you can prove anything you want. I can prove more than that. I can prove 3 equal to 4 if you want. That is a possibility to do. So that's why they make a big deal of it. It is a big deal only because of this. And that's why when I said, oh, now let me write this down. So that's why when I impose this problem, maximize no, sorry. Can you see that? Maximize u less than 1. Sorry. You see that? Maximize u strictly less than 1. You see that?
Yes.
So that when I said, if you tell me u equal to 0.9, I can give you a bigger solution, which is 0.99. If you give me 0.99, I give you bigger than 0.999, which means there is no optimal solution to that problem. So if you use that kind of idea, you can prove pretty much anything you want, and anything you want, you prove is going to be about garbage. So you need existence, otherwise you can prove all sorts of stuff that you which are not correct. So anyway, that's just the idea that I wanted to show to you. So in order for us to generalize the sufficiency condition, we need to define a concept of quasi-concavity. So let D be a convex set. A function psi defined on D is concave if psi py plus 1 minus p times z is bigger than or equal to its linear approximation, if you want to call it, for any p bigger than 0 and 1. So a function is convex, concave. All right, let me get a piece of paper. It's a good idea. And I should actually get a marker, which is maybe here somewhere. Concave. Oh, goodness. Marker is dry. So here's what I mean by this. You probably know everything here, but I draw a concave function, and I took 2 points y and z, and the right hand side is this point on that line. For any given p, the right hand side will give me a point on this line, and the left hand side will give me just about that vertical point, a point on the curve. You can see that the chord is always going to be below the function if the function is concave. So that's what 3.24 tells you. And now the function is quasi-concave if that that quantity is bigger than the minimum of these two guys. Okay, and that's called quasi-concave. And strictly concave means strict inequality becomes the inequality becomes strict inequality in 3.24, and you can have the function psi to be, if you take the psi to be concave or quasi-concave, then the minus psi will be either convex or quasi-convex. So we have defined the concept of a convex function, concave function, quasi-concave function, quasi-convex function. all the functions are defined on a convex set. Usually we don't define this function on a non-convex set because non-convex set can be disjoint, and it's not very interesting to define them. So we define them on a convex set. Okay, and that allows us to do the following theorem. We already know this one, but now we put a little thing on under the max. Let H0 be the maximized Hamiltonian, but maximize Hamiltonian that satisfies that constraint. So we define a function which is like this. Then let X star, U star, lambda, mu, alpha, beta, which is all part of the maximum principle, satisfy 3.12, which is the maximum principle. If H0 lambda t is concave in X at each time t, S, which is the salvage value function, is concave in X. G, which is the inequality, is quasi-concave in XU. A, which is strict inequality, is quasi-concave in X. And B, which is equality, has to be linear because equality is both concave and convex. So any function that is both convex and concave is linear. So even if I put B to be quasi-concave, it really means linear. Linear is quasi-concave. Okay, so that's linear in X. Then X star U star is optimal. So you notice now we did 2 or 3 things to the chapter 2 maximum principle, which is actually one of my row in my Nobel paper, which is the sufficiency condition done by Arrow. And you can see that sufficiency condition, Arrow did not do it for these constraints. He did it without the constraint, which is chapter 2. But in this book, we have this with the constraint. So if this is, and you can prove more or less the same way as the one we did before, but we are not going to do it. The proof is rather simple, but there's no reason to do it. It's one day maybe I will do that in exercise. Okay. So we have a sufficiency condition. By the way, quasi-concavity is a pretty strong concept, and it's not always clear, what kind of functions are quasi-concave. Because remember, that one is hard. That one is easier to satisfy than that one. So all quasi-concave functions are concave. But there are quasi-concave functions. No, all concave functions are quasi-concave. But there are quasi-concave functions that are not concave. So there may be all sorts of crazy functions that are not concave, but they are quasi-concave. And there are no way to characterize the geometrically, the shape of a quasi-concave function. So you don't see that shapes of it. There are many different shapes that will satisfy the definition 3.25. Okay. The next thing we want to do is very important, but it is not, how do I say it? It's basically algebra. It is just transformation of variables from one to another. It is not any mathematics in some sense, but it is useful in application in the sense that when we apply the maximum principle, and if there's a discount rate and we maximize the present value of profit, then it's useful to use this formulation than the standard formulation which we derived in chapter 2 so far, or chapter 3 also so far. So let's go with that. Let's find out what it means and how what the principle what the formulation is. So objective function in general is given by a function of x, u, and a t. The t in most application in our field, t appears only as a discount rate. That means at any given time t, the dollar value is discounted by the time in the future by the term e to the minus rho t. You don't see a t here unless the problem is seasonal. That means if the problem is seasonal, then December is colder temperature. February in Texas is now right now -5 centigrade or Celsius. And so you can have a function which has a, for example, if you want to sell Coca-Cola, the sale of Coca-Cola today will not be very high, but if you want to sell Coca-Cola in July, it will be very high. So sale of Coca-Cola given by function f may depend on whether it is July or December. But in many cases, we don't do that. And in many cases, we just consider the function to depend on only in x and u, and the time dependence only comes through the discount rate. Same with xt. Salvage value only depends on x, and this dependence on t comes through the discount rate. Okay? And so we have the objective function that looks like this. If you hear that blip, it seems to me that my fire alarm is acting up. Maybe it needs to change batteries. And it has a random phenomena. Sometimes it doesn't do it for 2 days, and then it goes for a few minutes. Okay, phi xu e to the minus rho t plus psi xt times e to the minus rho capital T. So that's our new objective function. And for this objective function, which is somewhat simpler, we can use the formulation in chapter 2 and the one we just derived. It's not a problem. But there is another formulation which is slightly easier to implement. But it is more or less the same, but it has slightly better notational aspect to it. So let's just do that. The idea is to define a present value Hamiltonian. The present value Hamiltonian is a discounted Hamiltonian, and this is the Hamiltonian that is the one that we use in chapter 2 and chapter 3. So in chapter 2 and chapter 3, f was this phi e to the minus rho t, and s was this. So we just use this. But since we are going to do a current value, we call the standard formulation present value. Okay? Because I'm going to use a lot of current value, I don't want to put superscript all the time CV. So I prefer the current value to have no superscript and the present value that we have derived to have a superscript. So the present value Lagrangian is LPV, which is basically HPV plus mu PV GXUT. And if we apply the formulation that we just derived, then lambda dot PV is minus LX PV. Lambda PVT is given by this. So we put PV everywhere, and we just apply the maximum principle. So the table that we have is all PVs, okay? Now what we do is we define a current value Hamiltonian. The current value Hamiltonian has a phi, but we don't put e to the minus rho t. So if we don't do that, we are actually dividing this right-hand side by e to the minus rho t. So the current value Hamiltonian is nothing but present value Hamiltonian divided by e to the minus rho t. When you divide e to the minus rho t on both sides, then you also divide lambda PV divided by e to the minus rho t. So I will define that division by lambda. So if we divide by e to the minus rho t and redefine lambda, then we get the current value formulation like this. And then the current value Lagrangian is like this. We define lambda to be e to the rho t times lambda PV. Remember, we are dividing by e to the minus rho t, which means we are multiplying by e to the plus rho t. Right? Dividing by e to the minus rho t is the same as multiplying by e to the plus rho t. So we are now multiplying lambda PV by e to the plus rho t, or dividing lambda PV by e to the minus rho t, you get the lambda. We also define mu the same way. So what are we saying? We're saying that on the scale from 0 to t, lambda gives me the marginal value of the state, x. But that marginal value was given in present value dollars, which is this lambda PV. And now I want to give you that lambda in the current value. Current value means the dollar at time t, not dollar at time 0. This lambda PV is the marginal value of the state at time t, the value evaluated at time 0. The new lambda is the current value of the marginal value of x derived in time t dollars. Okay, so the time t dollar is called the current value. Okay, so now we have that. And if you do all of that, we know h is e to the rho t HPV and L is e to the rho t LPV. So we have all the transformation. And now if you use 3.37, you take the derivative. Take the lambda dot, and on this side it will be e to the rho t times rho lambda PV plus this, that. You can take the chain rule and you get the equation, and you get lambda dot equal to this. Okay? Well, this term is nothing but rho lambda. And this term is nothing but minus Lx. So now we have a new Hamiltonian, which is the current value Hamiltonian. And we have a new adjoint equation, which is the current value form of the adjoint equation lambda. And we have a transversality condition. And we have alpha and beta. And we have a mu. So you can see we have sort of eliminated e to the minus rho t. When you do that, everywhere there is nothing e to the rho t except this part. We get a rho lambda. Instead of having a lambda dot equal to minus L sub x in the standard formulation, now we have a rho lambda minus L to the x. So now we have the maximum principle now can be restated in terms of current value formulation. This is the same. This now A is the current value, but the inequalities don't change because e to the rho t times this is the same as without e to the rho t. So it looks the same as before. This 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 looks the same as before. That one does not look the same as before. And the only thing changes is this part. We now have this part, rho lambda. So you can see we don't have to write e to the minus rho t all the time. If we apply the other one for this problem, we will have rho of e to the minus rho t all over the place. These guys will be all over the place, multipliers everywhere, and we don't want that. So we change to current value, and we have almost the same maximum principle. The only cost is we get rho lambda here. And that's okay. It's an adjoint equation. We can handle this or that is the same. Still, if this is linear in x, this will still be a linear equation in lambda. So it doesn't really. So this is what we use in current value formulation. Well, we need to do a few more things. In the current value formulation, that would be the same as the previous one. That one will be different. You see rho here? That's not there. That's not there in the previous formulation. So we see the row here, and we see row here when we apply for maximize over time. Just remember, these formulas are slightly different, but they are able to be derived from the previous formulas simply by dividing by e to the minus rho t or multiplying by e to the rho t. All of those can be derived. Just like I derived this part, just like I derived this one, you can also derive this one. You go from the previous equation 3.42. No, not 3.42. You go to this equation. Why did I put 3.42 here? Oh, it says it's by 3.42 and this, but this 3.44 is the current value version of this equation. This equation. You see alpha, beta, everything is same, but remember S sub t is not S anymore because S sub t was changed to psi times this. You see, S is now psi x e to the minus rho t. So initially it was S derivative of t, derivative of S with respect to t. Now, when you take the derivative, there is no derivative of psi x. The derivative only comes from this, which will be rho e to the minus rho t. But rho e to the minus rho t, we're dividing by that, so that goes away. And what survives is the rho. And what survives is the minus rho. So that's why you get minus rho here. So we just proved it. We just went from that to this one in one line proof. Any question there? Now, several examples. So we're going to start with examples. We're going to do first example to use the current value maximum principle. By the way, this example is going to be an important example because this example will run through the entire book. Every time we have a different formulation and different days, we'll use this example to illustrate something. And it'll go all the way to the stochastic chapter 12 or 11, chapter 12, when we will introduce stock market. Because right now, there's no stock market. This is savings account. Savings account that earns the interest rate of R. So the wealth is deposited in a bank, and the bank gives you the interest rate of R. So the wealth equation changes basically as consumption. So as I consume, my wealth goes down. As I earn interest, my wealth goes up. The net effect is W dot, which is given by this. So now I have an example in which an individual who wants to consume and utilize and maximize the utility of consumption along with the let me mention this. I put it here only for let me see. I put the value 0 here just so that it will be compared with other problems. But if you notice, if I maximize over CT to bigger than 0, this guy plays no role. Because our wealth is WT equal to 0. So the function, the objective function, which we had a salvage value, which had the XT in there, will have a WT in it. The WT is just 0. So remember, Chusha, right? She was asking a question about that function. She's this B0. We use this B0 using this SXT, this formula, right? Kind of this salvage value function. So now the X is fixed 0 and T is fixed. So this is not a function anymore. This is a number. It's a number given to us. that comes from that salvage value. You put 0 in there, you get that number, and you put t in there, you get that number. So this is just a constant that is not going to play any role in maximization. It will simply leave this. You just add this at the end, okay? The individual has a utility function, which is a concave function of consumption given by the log of C. This is quite a popular utility function because it makes the problem somewhat simpler to solve. And it's concave. And so we're going to just assume that to be utility function right there. The wealth dynamics is given by this. Initial value is W0, which we assume to be strictly bigger than 0. And this guy doesn't want to leave any wealth when he retires. Or no, when, okay, let's make it this way. This person is a deterministic problem, okay? And he or she wants to consume wealth to maximize the utility and just shoot for the moon, want to leave nothing. When he dies, he doesn't want to leave any wealth. But he knows when he will die, the t is fixed. In real life, the t will be stochastic. And then you have an expected value here. And that problem is also solvable. But right now, we are not doing that. We are not solving anything stochastic at this point. So we have a deterministic time t. The person wants to live with 0 wealth and consume everything that he's got. Okay? Or you can think of it this way. The person wants to retire at T, and he has certain wealth in a bank account, and he gets a pension. Like in many European countries, the pension is quite large, and people can just live on pension, and they don't need any wealth. So they can consume all their wealth before T, and then after pension, they just consume the pension. The pension is all the way until you die. So that is another way to look at it. But in any way, this is a math problem, and we're going to solve it. Because WT is bigger than 0, it is clear that at every other time, wealth will be bigger than equal to 0. This wealth will not become negative at any time, because if it becomes negative, there is no way to bring it back to 0. Because consumption can only be bigger than equal to 0, cannot be negative. And so without negative consumption, there is no way to bring the wealth. And if there's a negative wealth to begin with, the bank is not giving you any interest. The bank is charging you interest if you borrow money from them. And so there's no way to get back to WT equal to 0. There's no uncertainty, there's no stock market, there's no winnings. So this is the problem, okay? So that means that WT, which is the state variable, is going to be bigger than equal to 0. And so we don't have to put the constraint WT, small t, bigger than equal to 0, because it's automatically satisfied. Remember, if you put that constraint, then we don't know how to solve the problem. That's the chapter 4 constraint. WT is the state constraint. There is no control involved. It's a state constraint, and there is no way that we don't know how to solve the problem yet. It's chapter 4. But we don't need it. We don't need that constraint because it is automatically satisfied. So all these problems, even though they are simple, require some intuition, some argument of this kind to get us going. Current value Hamiltonian. Log C, remember I don't put e to the minus rho t anymore. Lambda times RW minus C. But because I don't do that, lambda dot is now rho lambda. The standard formulation, it will be simply minus delta is delta W. But in that case, we have to have this to be standard as well. That's a present value. So we get this. Remember, it's a fixed endpoint. So the lambda t is a constant to be determined. We have a freedom here to choose beta. Okay, so we will choose it. So let's choose that. If I choose beta to be beta, I solve the problem. See, I'm now solving a 2-point boundary value problem. The 2-point boundary value problem, W0 is 0. No, W0 is given W0, and W2 is given to be 0. So the both boundaries are on X. And there are no boundaries on lambda. Lambda is free, and lambda is free on both sides. So how do I solve the problem? Well, I make a guess. I make a guess for lambda to be beta. I make the guess on this side. Then I can solve lambda t. Remember, I don't need to constrain lambda 0. Lambda 0 can be whatever it wants. So lambda t is given by this. Lambda capital T is given by beta. And lambda 0 is given by, you put 0 here, okay? And you get the value of lambda 0. So those are all okay. The only thing is beta. We don't know what beta is. But look what happens. Yes.
Do you mind explain why lambda capital T equal to beta again?
Well, remember now, we in chapter 2, we only solve a free endpoint problem. That means in chapter 2, our problem was, let me see. If I do chapter 2, I would have to again do the screen sharing, right? Right?
Yes, if you open.
You don't see that? You don't see that?
Is it on the left of?
No. Do you see a graph?
No.
No. Okay. Let's not go there. But just to tell you, salvage value is the value of ending at X, right?
Mm-hmm.
So if I fix X, there is no salvage value.
Mm-hmm.
And if I fix X, there's no salvage value. So remember the free endpoint problem. The free endpoint problem, lambda t, was given by this formula. Lambda t was given by this formula, this part. This was not there because there were no constraints, okay?
Yes.
So that was the formula, but there's no S anymore.
Mm-hmm.
So lambda t can be any value it wants.
Mm-hmm.
But it has to be determined by all the other considerations that we will see. So let me spend one more minute, and I will need to do, I can spend a little bit more time on different ways of getting there rather than, but we're not proving that. We're not proving the maximum principle for this. So all we can do is give you various ways by which to justify this, okay?
Okay.
Yeah. So so I give you one justification, I'll give you more later. So the other justification is that if I fix lambda t, then I have W0, W2, and lambda t. I have 3 conditions. And I'm allowed to only have 2 conditions to solve those 2 equations. So if I give you 3 conditions, there's no way to solve that equation. So that's another way to say, if I were to give you any condition, I will not be able to solve this problem anyway. So the world is very nice to me. It allows me to do this so that I can solve the problem, but it turns out to be the necessary condition as well. So what we're now saying is that the mathematics itself tells you what not to do. And when it tells you what not to do, it leaves you only one option that you can do. And that only option you can do for which the problem is solvable has to be the necessary condition, because if it is not, then there is no way to solve the problem. It is almost like saying, Descartes' way of saying, the world exists because I am here. because if it didn't, I wouldn't be here. So if I could do anything else, the problem is not solvable. So it has to be this way. So that's another way. But we'll talk more about it as we go along. Okay. So then what do? We only have now two conditions, here and here, and these two conditions are free, so we are able to solve the problem. So let's see how we solve the problem. We assume beta to be beta, whatever that is, we just fix it to some beta, and we now determine what it is. When we fix it, we get this. But remember, it cannot be, it has to be some value. It cannot be any beta. It has to be something that will come out of fixing these two boundary conditions. So I want to fix those two boundary conditions right now and determine this beta. Okay, that's solving a 2-point boundary value problem, but not by Excel, but analytically. Okay, so now see what is the optimal solution? Delta H delta C. I want to maximize the Hamiltonian. So if I do delta H delta C, it is 1 divided by C minus lambda. So that has to be equal to 0. So the C star has to be equal to 1 by lambda T, right? But we already know what lambda T is. So lambda T is given by this. So I put 1 by beta like this. So I know C star T, but in terms of beta, I don't know the beta yet. But whatever beta it is, that is the C star T. So now, because this is my optimal consumption, I can find the optimal wealth path. So W dot equal to RW minus that optimal consumption rate, and W0 equal to 0. If I solve this problem, it's a linear differential equation of first order. The solution is W star T equal to this. There's a beta here. How do I determine this beta? By fixing the boundary conditions. So I put capital T here, and I put that equal to 0, right? Because W star T has to be 0. That's what our problem says. WT has to be equal to 0. So I set W star T equal to 0 here. Here. That gives me beta equal to this. That's beta. That is the only beta that will give me W star T equal to 0. You see what I'm saying now? You take the beta, solve the differential equation, and find that beta that will give you the boundary condition, because I already have W0, but I don't have a WT yet. But I have a WT equal to 0. So WT set equal to 0, get the beta. So I have the beta. Okay? And once I have the beta, I can put that value of the beta here. I have a consumption. And I can put that consumption in there. And I can integrate. And I can actually give you the objective function value. So objective function is J star integral of log of C star, which is given by this, and the B0 e to the minus rho t, which is sitting there, which I add back, and I have this objective function. And I also have a lambda t, because lambda t was in terms of beta, but I now know the beta. So I put the beta in there, and I have a lambda t. Sorry. So we are only allowed two boundary conditions if they are fixed boundary conditions in two differential equations. If you solve two equations, you are not allowed to have more than two boundary conditions. If you only have one boundary condition, you have too many solutions. If you have two boundary conditions, you are lucky to be having one solution. If you have three boundary conditions, you will not have any solution. So if one boundary condition in two equations, the solution is underdetermined. Underdetermined means many solutions. You cannot find out which one. There are many. Two means it's completely determined, properly determined. Three means it's overdetermined because there is no solution for it. If there's no solution for it, and we are looking for a maximum, we are looking for a solution. So that's all we can do.
Hi, Professor. A quick question. So we had lambda capital T equal to beta, but if we assume lambda 0 equal to, let's say, alpha, then we can also solve the problem with same logic, right?
You can also do lambda 0 equal to alpha, and you can still solve the problem. That is that, but then lambda t cannot be. But that can be done. You can do that if you want.
Okay.
It's not a problem. But that's solving the 2-point boundary value problem. In
Yeah.
maximum principle, lambda t is a value of the marginal value of the state. It has an interpretation. Okay? Lambda 0 is the marginal value of the state at 0, but state at 0 is given to us. So you're right. You can do it the other way if you want. It's okay.
Okay, thank you.
It's fine. Because essentially you are solving, if you were to solve the two equations and you have two boundary conditions W0, Wt, then Excel, you can do this way or this way. You can guess lambda 0 and continue, or guess lambda t and continue, right? Either way is fine. It's okay. But that's how we write the maximum principle, because in maximum principle, we have something called the transversality condition, and that condition is only for lambda t. That's how we give it. But remember remark 2.9 or 2.8? 3.9? It tells you something about that as well, right? It says you can solve the problem. You can just assume time to be reversed. You can write the maximum principle in which lambda 0 will be beta to be determined. You understand? If I make capital T equal to 0 and 0 to be capital T, then I'm going in the other direction, right? I write the differential equation in minus T. That we will do that actually later. Later we will solve the problem in chapter 5. We will solve the problem doing that. We'll actually solve the problem starting with capital T and going all the way to 0 and solve the boundary condition that way. We will see that too. So by that time, you will get a little bit more sense of what's going on. Okay? So you can see Sx0, Ax0, Bx0, and then there will be, because x0 is fixed, you can say lambda 0 is a constant to be determined. Yeah, you see here, right here? You see this lambda 0 is x0? You see that one? You see this
Yes.
is, you see, if I would formulate the problem this way, I have lambda t is like this, right? Right? If by remark 3.9, I reverse the role of capital T and 0. So now my lambda 0 is given by this, right?
Mm-hmm.
So what you're doing is formulating this problem, 3.9 problem. If you do remark 3.9, you can assume this to be beta in a fixed line price. And then you can, just like we changed this to beta, because Wt is fixed, we can now change this to beta because W0 is fixed.
Yeah.
And then we can solve the problem that way. So that's essentially the same, but yeah, if you want to do it, you can do it. Okay. I mean, this problem is really godsend. It will give you a lot of insight into the optimal control problems as we go along this problem one by one. We will see this problem maybe 3 or 4 times before we finish this course. Different form, different version, different modification of this problem to give you some idea of what's going on. For example, I will ask you next time, what if Wt is not 0 but bigger than or equal to 0? That's a different problem, and we will solve that problem later. You will see. And it has a very rich economic interpretation. It basically says that in order for me to maximize my utility by maximizing my consumption in some way, because I'm actually consuming like there is no tomorrow. Tomorrow being capital T. Tomorrow being capital T in this case. Because I don't want to leave any wealth at capital T. So I want to consume a lot. And this condition says if I consume a lot, it must be consumed in that style. But if I consume in that style, I want the beta to be so small so that the consumption is so large so that when I do that consumption, I leave no wealth at the end. Do you see what I'm saying? Yeah. So that's why beta can be, if beta is large, it means I'm consuming too little. If beta is small, it means I'm consuming too much. And my wealth will be less than zero. If beta is too large, I will leave the positive wealth. That means I will not consume everything and I will leave something for the children. So beta has to be exactly right for me to have the wealth exactly equal to zero at capital T. That's the 2-point boundary value problem for you. Now I will tell you that if I give you W2 bigger than equal to zero, it's neither fixed nor variable, right? It's halfway fixed. So when you have a 2-point boundary value problem, it's halfway fixed. It is not exactly two conditions. It's not exactly two conditions. So you will see what we mean by that later. If it's halfway fixed, I need another halfway fix somewhere else. Otherwise, I don't have enough condition to determine. You see what I'm saying? So let's get there. I think it's a good discussion to get the intuitive idea of what are the boundary conditions. A, they mean mathematically, because without them, we cannot solve the problem. B, they mean economically. They have meaning, very rich meaning, economic meaning of why they are there. Arrow calls them dynamic foresight condition. Foresight means lambda t has to have that value so that in the future, I will end up with what I want to end up with. Now, this one was added, and if you have a chapter, don't look at chapter 3 for at third edition, because third edition had a typo in this particular formulation, so I fixed it. And it is a little bit complicated to show it, but I want to show it anyway. So what I'm trying to do is this. We found the current value formulation of this problem. But remember, we derived the maximum principle by using a dynamic programming equation, which we call Hamilton-Jacobi-Bellman equation. So if I have a current value maximum principle, there must be a current value version of the Hamilton-Jacobi-Bellman equation, right? So the value function in chapter 2, value function V, was present value function. The value was in dollars at time 0. What if I do the value function in a current value formulation? And if I do that, what is going to be the Hamilton-Jacobi-Bellman equation? And this is what I'm going to do next. And I think this is all we're going to be able to do today. So let's go through this. There are many ways to do it. It is not difficult to derive this equation, but I am deriving this equation slightly different way, because one way to derive is simply to define this equation. See this equation here? This is the present value function, right? This is chapter 2. And the current value function is nothing but e to the rho t times that. Because if I want to bring the value from $0 time dollar to t time dollar, then I have to multiply by e to the rho t. Okay. In other way, the current value has to be discounted by e to the minus rho t to bring you the present value. And I already know the equation of this guy. So if I multiply this, I can easily derive the equation for this guy. This is one way to do it. It's a straightforward, just like we did the Hamiltonian. But I am now going to do slightly more complicated way. So you are welcome to define this V and go to the Hamilton-Jacobi-Bellman equation, which is going to be exactly the equation that will look like. Where is the equation, by the way? Well, we only derived this 3.55 and this condition here. So this is your equation. That was the equation in chapter 2. Chapter 2 equation is, rather than going into chapter 2, which I cannot do, I will just ask you to look at the equation that we derived. So we derived this equation. The value function was derived in section 2.2, and it looks like 2.15. So if you look at 2.15, you will see an equation that looks like 3.55. But 3.55 is the current value version of the equation 2.15. 3.55 is the current value of 2.15. It's already written there. I'm sorry, it's already written there, 2.15. So you have the ebook with you. You can easily go to 2.15 and compare this. I don't have without sharing. It's difficult to show. Next time I'll share the window. I have like 10 windows open. I'm working on certain things. So okay. So the current value Vxt. Now I'm going to define the current value. So I'm going to do from the definition rather than transformation, which you can do from here. The answer would be the same. So what do? Let's define the value function, current value function. The current value function is a value in time t dollar, starting from t, small t, to capital T. That is my objective function. Discounted 2 times small t, not all the way to 0. So you see it's rho s minus t. I am now at time s. When I'm at time s, to bring that time to capital small t, it will be minus rho s minus t. Okay, that's clear, right? Because this is small t, this is s. So I have to bring only up to this time, and this time is equal to s minus t. So I have to multiply e to the rho times s minus t, and then the minus thing. Okay. Same thing. My terminal value have to be go from capital T to small t. So I have to take the derivative. I have to discount to that. So this is my definition of the current value objective function. If I knew this, I can do this. But right now I'm deriving this from first principle instead of going through VPV and do the transformation. Okay, so this is this if xt satisfies these are all. If they don't satisfy, then this is equal to minus infinity. That means if the solution is not feasible, then the value function is really bad, and the really bad when you're maximizing is minus infinity. Okay, Well, what we did, we start from t, and then we go to t plus delta t. Okay, so we now go to t plus delta t, and so I go value function equal to max t to t plus delta t, same thing. Then e to the minus rho delta t, because I only go from t plus delta t to t, so the derivative has to go only, discounting only goes from just delta t, so it's minus rho delta t. So it's e to the minus rho delta t. And then in at time t plus delta t, I have a value function again, which is the current value function again. It's v of xt plus delta t and t plus delta t. You should go back to chapter 2, section 2.2. You will see that this derivation is almost the same as there, but these, because the discount rate is coming all over the place, it looks a little bit more messy. The next place is interesting. E to the minus rho delta t can be expanded this way. 1 minus rho delta t, a little o delta t. We did remember there was a o delta t was going to go to 0. That's how we derived that equation. So now we have to do that too. So when I substitute this, and I can see the version, you see it's 2.15 and 2.19. So you can sort of see, 2.15, 2.19, and then if you go here, I'm sorry. Yeah, so delta t, we can obtain the current value version. So I do this, and I get this. Then let delta t go to 0, I get this. So you see this rho is coming here. In 2.15, this was 0. And because of this e to the minus rho delta t, which has this Taylor value extension, I get this rho delta t term. 1 and 1 is v, so that v and that v, that there was a v in there, that those cancel out. So v and v canceled out, just like in chapter 2. But that rho delta t is still not O delta t. When you divide by delta t, the rho survives, and that becomes rho vxt. So this is almost similar now to maximum principle. This rho survived, and this is rho lambda. Remember, lambda dot is minus Lx, now it's rho lambda minus x. Okay. So I have a new current value formulation of the Hamilton-Jacobi Bellman equation, or Hamilton-Jacobi equation, Hamilton-Jacobi Bellman equation, because of the max. And if this is not satisfied, then it's minus infinity. So I am doing a little bit more than chapter 2. In chapter 2, there is no minus infinity because everything was feasible. There were no constraints. But now there are constraints. And so I'm giving you, if there are constraints, the value function has this kind of form. Usually this and that. Same this, and it's minus infinity otherwise. So, okay. So, free endpoint, that means yt is the set of all feasible solutions, which is free endpoint. Then lambda t is just the derivative of the salvage value function. And lambda t equal to 0 if psi is 0. So you see, if psi is 0, then lambda t is fixed because it's a completely free endpoint problem. If it's a fixed endpoint problem, then terminal state is xt minus k equal to 0. Then terminal conditions do not provide any information on lambda t. So lambda t will be some constant of beta. But the terminal condition is fixed, so there is no more information. I have to end up there. So that's another way to see that if there's no information, then lambda t, I cannot tell you what lambda t is. So it has to be determined by some other consideration. Here's a halfway kind of thing. So if it's a halfway, that means there's a lower bound. Xt is bigger than or equal to k. Now, if xt is bigger than or equal to k, then I don't have exactly xt. So if I don't have exactly xt, I have to make lambda t free, because otherwise the system is overdetermined and I have no solution. But now xt is bigger than or equal to k. So I have a freedom to go beyond k, but I don't have a freedom to go below k. So I don't have enough boundary conditions. But if I put lambda t bigger than that, then I'm also giving lambda t a little bit room to play. Because there's a room to play here, I need to place some room here. Otherwise, the system will be overdetermined. And that also comes from the complementary slackness condition that we talked before. And here's the complementary slackness condition. So that gives you a 2-point boundary value problem of more complicated type. And we will solve 1 or 2 problems later. Okay. So, and with the shadow price, so the shadow price of inequality constraint 3.4. So case 3 lower bound. So we have this on lambda, but also with the lower bound, we have alpha, and alpha is bigger than or equal to 0. And for psi x identically equal to 0, we have this condition. It's upper bound, it's just the opposite. So I don't want to spend time on it. You can always ask me a question and I can do it. And the general case, again, comes back to the same general case. We had this condition before. So it is same as 3.4, 3.6. I want to stop here at this point. I want to do this and then I will stop. There are conditions sometimes. There are conditions sometimes where you have a budget constraint. So suppose if I use x and u, suppose I'm at x at time t and I use u, then the amount of money I need in order to implement u is Lx of ut. And if I have a finite amount of money, let's say k amount of money, then I cannot exceed that. So the integral of all the money I spend has to be less than or equal to k. Such constraint in mathematics are called isoperimetric constraint. In our model, we call it budget constraint. How do we solve this problem? Because we did not do in chapter 2, and we have not done in chapter 3. But we don't have to worry about it. What we do is we introduce another state variable, xn plus 1, and we define x plus 1 dot equal to minus of L. So that xn plus 1 is the remaining amount of money. So at time 0, the remaining amount of money is k, because you haven't spent anything. And at time, as we spend the money, this x is going to decrease. And at time t, it will decrease to xn plus t. And we are required that we don't exceed k. That means that the money that is remaining at the end of the problem time has to be bigger than or equal to 0. That means I cannot overspend the budget. Xn plus 1t cannot be negative. So that means I overspent the budget. So as long as it's bigger than or equal to 0, I either spent the budget or I did not. I left some money at time t. I did not spend all of the budget. So when it says k less than k, it doesn't mean you have to spend all of your budget. If you spend all your budget, you have to spend all your budget, then this has to be equal to k. Then this has to be equal to 0. So that problem can also be formulated as a problem that we already used to know how to solve. And all of that I've done in terms of boundary condition or transversality condition, we call them, is all summarized in this table. This is the general setting. These are various special cases. And this is the lambda t. And this is the lambda t for psi equal to 0. So this table has all the transversality conditions that you will need. And if you don't remember these conditions, then it's good to have this table with you, and you can consult it. And it's a good place to go. And now we're going to solve that problem, which will be done next week. And so next week, please go to chapter 4, because chapter 4 is very difficult chapter in some sense. Even though there are no proofs, it's got a lot of stuff. And the problems of state constraints are not easy to solve. Even if you have algorithms and computers and stuff, they are still difficult to solve. But they happen, and we need to deal with it. And so do read chapter 4 very carefully, and have set of questions that you don't understand, and so we can clarify them next time. And of course, we will continue to do chapter 3, which is not finished yet. There are still many things to go in chapter 3. So we will start at this table next week. Other than that, I hope that you will stay safe and have enough stuff in your house in case the power goes down today, because tonight is going to be colder than yesterday night. And so I'm basically dreading, houses here. You can get a pipe burst when the freezing happens. So all my outside, not outside, but the wall the faucets that are on the outside wall, I am setting them at a drip, and they are dripping, and all the water is going waste in some sense. I'm collecting some, but I can only collect so much. And that's to avoid pipe from freezing and bursting. Anyan's house, Anyan was in China last time, and his house had a leak, and the pipe burst, and the house got flooded, and he got a lot of insurance money to repair it. Almost $30,000 the insurance company gave him to fix his house. And now again he's in China. I mentioned to him yesterday, I said, please tell your neighbor to go to your house and set the drips, and so that the pipes don't get burst. But anyway, that's Texas life right now. Okay, if there are no more questions, I would say bye for now. And thank you for coming to this class, even though the university says you don't have to. And I had to go all the way to the associate dean to make sure that I am not doing anything that I should not be doing. So I needed some approval, or you say, oh, why not do it? So I said, okay, as long as you said it, I have an excuse. And if somebody bothers me, I can say, Varghese told me this. So, and you guys approved it anyway, so everything is fine. Okay, thank you very much.
Thank you,
Talk to you later. Bye-bye.
Thank you, sir. You have a good day.
Thank
What'd
you,
you say?
Professor.
Oh, the homework. Yeah, did homework. Let me give you the homework. Homework is 3. No. Homework is 3.19, 3.35, and 4.10. Got it? 3.19, 3.35, 4.10. I think Gautam will send you email anyway for the homework. So, okay, thank you. Bye-bye.
Thank you. Bye.
Thank you,
Yes.
Professor. Bye.
Thank you. Bye.
Yeah, bye.